How do odds work? Positive odds signify underdog. Plus 102 means that a $100 bet on Packers will win $102 if Packers win. That is, you get $202. The $100 you place is returned and $102 on top. Negative odds signify favorites. So negative 122 means a $122 bet placed will win $100. That is, you get $222, which includes the $122 you spent and $100 on top. This is also called the money line and is what I will be using for my project. The code for our cost function looks like this. If our prediction is correct, we check which fighter is predicted to win. We then check if the fighter's odd is positive or not. If positive, then we have an underdog, so we add the odds to our bank account. Otherwise, we add 100 over absolute value of the odds, since that is how favorite odds are paid out. If our prediction is incorrect, our bank account loses the bet amount of $100. Betting odds will change. Sportsbook will adjust their money line to ideally get half of the bettors on either side. That way, loser pays winner after Sportsbook takes the share. Other factors that moves the money line are new information such as injuries. Line shopping is when bettors monitor the money line across different betting sites. For my project, I have scraped the maximum value, which is the best payout for both underdogs and favorites. Line shopping can be done using websites such as Best Fight Odds. Check out my video on how to scrape bestfightodds.com. Link is in the description. An arbitrage bet is when two bets are placed such that you are guaranteed a payout. In this example, we place a $57.90 bet that Team A wins and a $40 bet that Team B wins. In either scenario, we win $100 since both bets are exhaustive. Exactly one team wins, there is no tie. It should also be noted that betting companies that are able to detect such behaviors can cancel the bet before the event when it is legal to do so. They can also warn or ban accounts. A middle bet has three cases. One case where one team scores over some number of points, another case where the other team scores under some number of points. The final case is the middle bet where both events occur. We will be using ELO scoring as a feature. The favorite should have a large value and the underdog should have a small value. If our underdog David wins, he should gain huge amount compared to if Goliath wins. ELO scoring is a zero sum, so winner's ELO score increases by exactly what the loser's ELO score is reduced by. We assume each fighter has some unknown ELO distribution. Although we do not know what the distribution looks like, we assume the center of each fighter's ELO distribution is their current ELO score. For any fight, both fighters draw a number from their ELO distribution. The fighter with the larger number wins. Here, the blue fighter is the favorite and red is the underdog. We see that blue should draw higher numbers more often than red. But some days, the underdog will perform better than expected, so red will draw a relatively higher number. That is, blue happens to draw a relatively lower number for that match. Our red underdog will end up winning the match. We actually want to train our machine learning model to be able to predict when an underdog will win, since this is when the best payouts occur. ELO was originally developed for chess tournaments. This adaptation was borrowed from 538 NFL. We will convert our method of victory column into our ELO column. So a weight of 5 will be awarded if finisher was used, such as a knockout or submission. 3 for a unanimous decision, 2 for majority decision, 1 for split decision. We could run into a problem where a fighter that is good at finishing fights can also have their ELO score quickly overinflated, so autocorrelation should be used. Here I use test, train, split, and logistic regression. The plot shows I ran multiple degrees of 5 between 5 and 30 and chose the one with the highest accuracy, which is degree 10. It should be noted that since test, train, split is random, data leak can occur. More on that later. Now that we have our data, we need to pre-process our data. The primary approach is to take all of the blue fighter's career statistics and subtract the red fighter's statistics. We then convert our winner column to 1 if blue is the winner and 0 otherwise. To utilize the stance column, I decided that if blue was southpaw and red is orthodox, the value should be 1. If blue was orthodox and red was southpaw, the value should be -1. I am not familiar with the other stances, so everything else will be assigned 0. Missing data was initially imputed using NumPy not a number mean, which calculates the average while ignoring not a number values. When it came time to actually train the models, I realized that I should not have used data that was not available prior to the fight, such as total fight time. This is because inferences can be made such as if a total fight time is the maximum value, we know a decision was made. Otherwise, we know a finisher was used. Other missing data such as average, significant strike, or a takedown percent difference was assigned 0, so neither fighter is given an advantage when data is missing. Feature selection consists of calculating the correlation matrix. Take the maximum pair and choose which feature of the pair to drop. We repeat the process until all correlations are below some threshold. When training our model, we want to avoid train, test, split since it is a random process. Being a random process means we can have a situation where we train using future statistics to predict past outcomes. For example, if we train on a fighter who has won 2 out of 2 matches and we want to predict the outcome of their first match, we already know that fighter has won the first match. Our data is sorted such that the newest is on top, so we will train all models on data below row 200. Python uses a 0 index, so that will be row 199. We will simulate bets in chronological order, that is, we predict matches from 199 towards 0 and place bets if betting odds are available. For each model, we also subset our data by weight class and train a model for each weight class. I am assuming each weight class is different enough to need their own model. It seems like women's strawweight are less likely to knock out their opponent than men's heavyweight. This also takes care of differences in fighting style between the genders. Here is what the betting function looks like. We take in as input some machine learning algorithm. The function initializes an empty dictionary and uses weight class as the dictionary key. After training our model, we save the model as our dictionary value. We simulate a starting bank balance of $5,000. Iterate from 199 towards 0 inclusive. If betting odds is an integer for that row, we can simulate a bet. We pull up the trained models for that fight's weight class from the dictionary. Using the model and data that would be available before the fight, we make a prediction. Betting on our prediction, we calculate our new bank balance using the previously discussed cost function. If betting odds is not a number, we copy the bank balance forward. Finally, the function returns our bank list of our betting simulation. Looking at a section of the data that will be used in our simulation, we see some odds are greater than 200. We could change our approach to focus on more profitable models. Let me know in the comments if that is the approach that you tried. We also note some fights do not have an underdog. It should also be noted that if you sum across the rows, you will see that the odds sum to a negative value, which suggests that our cost function adds up to a losing situation for gamblers. So let's find out if machine learning can be used to make a winning situation. K nearest neighbors classifier is computationally expensive to implement since I use brute force to get the best number of neighbors for each weight class. The proposed number of neighbors are all odd numbers between 1 and 19. Since neighbor values and weight classes do not depend on previous calculations, I ran them in parallel, which my computer is set up to take advantage of. I uploaded to Kaggle after I had finished the notebook on my computer. At that point, I just hit the run all on Kaggle and check back later. My initial models lost money. K and N performed best, and it is the only one that had a tune so far. Logistic regression went negative since I did not implement a stop at bankruptcy. Here is a look at the accuracy of our models. When we narrow down the accuracy to the proportion that correctly predicts underdogs, we see that the percentage is very low. Looking at the proportion of data where the underdog actually wins, we recognize that this is an imbalanced data problem, so that will be my approach to improving the models. Later on, we see that accuracy is a misleading number. By training on events when the underdog wins, we see all models again are losing money, but accuracy is higher than our previous models. Here, decision tree and logistic regression will have almost 75% accuracy. When we look at proportion of accuracy that belongs to winning underdog, we see 0%. So we interpret this high accuracy as having a model that is really good at predicting when an underdog does not win, which is not useful. Notice that some plots appear to be missing. This is because you cannot see equally worthless plots when they are exactly on top of each other. Here we see changing the weight class for logistic regression showed some improvements. On the left, I gave balanced argument a try. On the right, I tried searching for the weight values in 2 passes. First pass was in increments of 10% weights. Since 90% had the best result, I made a second pass with increments of 1%. After tuning logistic regression, we see downsampling, majority class, and upsampling using SMOTE resulted in models that made money. When we applied downsampling and upsampling with default logistic regression, we got a flatter model, which is better than losing large amounts of money. Going over the downsampling code, in every section I reloaded my data as if every section was its own notebook. Y vectors will have the winner column since that is what we will be predicting. We also have underdog win column for downsampling, which will be dropped after downsampling. The minority class will be when the underdog wins, and the majority class will be otherwise. Since X and Y vectors are of the same subset of the same CSV files, we will use Y vectors index to select our data since that vector is the one that has the column of interest. We then use the resample function from the scikit-learn utility library to sample without replacement. I tried 1-to-1 ratio, half and 3/4 ratio. Seed should be used for reproducibility, otherwise you will get different results. We then concatenate downsample with the complete minority class. We drop the underdog win column as it is no longer necessary. The rest of the code is the same as before. SMOTE only requires a few lines of code. Ytrain is the column we want to upsample. Initialize SMOTE with seed for reproducibility. Call the resample method and pass in the vectors we would have passed into algorithm.fit. Pass the upsampled vectors into algorithm.fit. This video was a brief summary of my Kaggle notebook. Link is in the description.